Good afternoon, I'm Yoichi Murakami from Tokyo Institute of Technology. Today I'll be talking about thermo-electrochemical conversion integrated into forced convection cooling. As the background, active cooling is needed in broad situations in our world. For example, heat engines essentially require cooling on both low temperature side to increase the efficiency and the high temperature side to protect materials. For electronic components such as microprocessors, cooling is done to prevent failure, whose rate exponentially increases with temperature as shown here. The thermal energy or heat generated in such situations is often regarded as wasted heat as a target of thermal energy harvesting. However, it is important to make a distinction between two types of essentially different heat. The first is heat already released to outside the system, which is heat reusable without the duty of cooling something. This is a pure resource, such as warm water released from a power plant. The other type is heat being dissipated inside the system, which is heat accompanying a duty of active removal and cooling. This is undesirably generated in a system and must be removed promptly. Here I explain what is lost during the cooling. Actually, active cooling is a fast transfer of thermal energy under a large temperature difference. As graphically shown here, the thermal energy of amount of ETH that was initially inside the heat source at T hot has an exergy of this amount relative to the environmental temperature TENV. Here the exergy means free energy portion of thermal energy convertible to work. After this thermal energy is transferred to the coolant liquid as the heat of Q, this same thermal energy, now at lower temperature at T liquid, has smaller amount of exergy due to the decreased temperature. So as a result of the second law of thermodynamics. Therefore, the forced convection cooling greatly widespread in our world is tantamount to a rapid destruction of exergy of thermal energy. This issue has not been addressed previously. To address this issue, we had an idea of integrating forced convection cooling and thermo-electrochemical conversion. The latter is an existing technology in which a closed cell containing a redox-active liquid generates a term voltage that arises from temperature difference as shown here. This is conducted without flow of liquid except natural convection in the cell, aiming to harvest the freely reusable heat without a duty of active removal. Therefore, the proposed technology is cooling plus power generation. However, such a technology is not well studied yet, and many aspects such as feasibility, design strategy, and characteristics have to be elucidated. Especially, we have to answer the basic question whether we can generate more electrical power than the pumping work required to force coolant through the cell, or whether the gain can be larger than 1. When we started this project several years ago, we adopted the microchannel concept as the design strategy of our cell. From the basic knowledge of heat transfer, the heat transfer coefficient H is given by this formula, where the hydraulic diameter dH is in the denominator. Because the hydraulic diameter of a channel formed by two parallel plates are twice of its spacing, we can predict that as the gap becomes smaller, H becomes larger, resulting in more efficient cooling to the wall. This is the concept of microchannels, as investigated by several previous papers, including my past papers worked with Professor Bora Mikic at MIT. Therefore, the novelty of the present study lies in the combination of forced convection cooling and thermo-electrochemical conversion to create a system whose main purpose is cooling, but at the same time generating electric power more than the pumping power to force the coolant through the cooling section, namely self-contained cooling system. It is emphasized that the use of microchannel concept is expected to be triply advantageous. They are first, large interelectrode temperature gap by thermal boundary layers, from which large thermoelectric voltage is expected. Second, facile interelectrode mass transfer because of the short distance, from which large electric current is expected. And third, large heat transfer coefficient because of microchannel effect, from which efficient cooling is expected. This slide shows the test cell we developed. As shown here, this is a small cell having the outer dimension of 6 cm by 4.5 cm. The liquid flow inside the cell is shown in these graphics. The electrolyte liquid, which is an ionic liquid solution of redox couple shown here, first enters the cell from the bottom and goes to the left, and then enters the microchannel formed by two flat electrodes, anode and cathode. Here the cathode simulates an object to be cooled, and the temperature was controlled by a ceramic heater. The anode is a platinum plate as shown here. Here we investigated two types of cathodes shown here. The cathode number 1 forms a narrow channel of only 0.8 mm spacing, while the cathode number 2 forms a wider spacing of 2.2 mm. This graphic shows a cross-section of the simulation domain where cathode number 1 is installed. To predict the temperature distribution inside the cell, we carried out numerical simulations described here for cathode number 1 at a flow rate of 0.49 ml per second, corresponding to the liquid speed of 30 mm per second. As shown here, our simulation predicted that for this typical experimental condition, a large inter-electrode temperature difference of 130 Kelvin is achieved for 0.8 mm gap due to the thin thermal boundary layer. First, I show the effect of electrode spacing on cooling performance. These figures show the dependence of removed heat and heat transfer coefficient on the temperature of the cathode. In both figures, the use of cathode number 1 with 0.8 mm gap showed better performances. Therefore, the effectivity of the microchannel concept was verified, and relatively high heat transfer coefficient of 600 Watt per meter square Kelvin was achieved. Then I show the dependence of electrode spacing on the power generation performance. In this figure, the values on the vertical axis represent short circuit current, and values on the horizontal axis represent open circuit voltage. From this IV curve, because the power equals current times voltage, we can obtain maximum power Pmax as shown in right figure. From these results, advantages of using a narrow gap, which is expected to enhance the inter-electrode mass transfer, was verified from this increased short circuit current. Also, we found the enhancement of delta T, which is proportional to the generated voltage, was smaller than expected with cathode number 2, resulted in an overall excellence of cathode number 1 over cathode number 2 for the power generation performance. Here it is noted that from the open circuit voltage and reported Zwick coefficient for the redox couple used in this study, which is 1.6 mV per Kelvin, the average temperature difference between anode and cathode was found to be 125 Kelvin. This is a very large temperature difference for the 0.8 mm distance, agreeing well with the result of our simulation that predicted the temperature difference of 130 Kelvin for the same condition. Next, I show the dependence on the cathode temperature for cathode number 1. Here the left figure shows the IV curves and the right figure shows the relation between Pmax and delta T. We found that as temperature of a cathode increased, the open circuit voltage increased because the voltage is proportional to delta T. And as temperature of a cathode increased, the short circuit current also increased because the mean viscosity in the channel decreased due to the higher mean temperature there. Then I show the dependence on the flow rate for cathode number 1. Although a bit complex, as the flow rate G increased, the open circuit voltage increased because the temperature of the cold side electrode decreased. In addition, as the flow rate increased, the short circuit current slightly decreased because the mean viscosity in the channel increased because of lower mean temperature there. These features resulted in, as shown here, a monotonous increase of the generated power with increasing the flow rate. Next, the performance measure of the present system is discussed. First, in conventional thermoelectric systems, including solid devices where cooling is not intended, the efficiency is given by the generated power divided by heat passing through the cell as shown here. The evaluation by this method is reasonable because heat is purely resource in this situation. On the other hand, in the present system where the main purpose is active cooling, an application of conventional efficiency, which is on the order of 10 to the -5th if applied, contradicts to the purpose because more efficient cooling, which results in larger Q, leads to a worse evaluation of the performance. Thus, appropriate performance measures for these systems need to be considered, which is shown in the next slide. As an important feature, this system requires a pumping work to operate. The hydrodynamic pumping work is flow rate times pressure drop across a cell. Therefore, we define the gain lambda as shown here. It is noted that pressure drop could be accurately determined using our simulations because the flow inside the cell was highly laminar. As shown by this figure, the lambda monotonically decreased with increase in the flow rate. However, below some threshold flow rate, the cell generated more electric power than the pumping work required to force the liquid through the cell, demonstrating the feasibility of the proposed concept. To summarize, we have successfully achieved an integration of thermo-electrochemical conversion into forced convection cooling, which have developed separately. We emphasize that microchannel concept is highly beneficial in this system. In particular, we have demonstrated the inter-electrode temperature difference of about 130 Kelvin could be achieved in the steady state in 0.8 mm distance, achieving open circuit voltage of 0.2 volt. We have also demonstrated that the generated power can exceed required hydrodynamic pumping work, namely the gain could be larger than 1. This result has demonstrated that this proposed concept is feasible in principle. However, I also mentioned that the generated power was limited, where the power density was on the order of 1 watt per square meter, which needs to be increased up to 100 times at least for the future use. We have been pursuing this improvement, and recently we have succeeded in substantial increases of both the generated power and gain, which will be presented elsewhere soon. Thank you for your kind attentions. I welcome to accept your questions by email. The email address is shown here. Thank you again.